Question 3b, still of past question 2018-2019. A cylinder contains 0.5 meter cube of steam at 4 bar and 200 degrees Celsius at 4 bars. If the steam is cooled at constant pressure to a volume of 0.1 meter cube, calculate I, the final quality of the steam, II, the work done, III, the heat transfer during the process. So I said this earlier, that whenever you hear final quality of a steam, it simply means you should calculate for the dryness fraction, X. Okay, let's do that. Question 3b. First thing first, we list out our parameters. Here they said at initial condition, let's get the initial condition since it involves two processes. Okay, initial condition. Initial condition, we have that V1 is given as 0.5 meter cube and P1 is given as 4 bars, and finally our temperature T is given as 200 degrees Celsius. So next thing, we have to check if it is a superheated or saturated steam. So how do we search if this is a superheated or saturated steam? So let's go to our saturated steam table. We know that at 4 bars, what is T sat? Let's check for that now. At 4 bar, if our temperature is given as 200 degrees Celsius, then we say that the steam is saturated. Or if it's given below 200 degrees Celsius, we know that the steam is saturated. But if our Tsat is greater than 200 degrees Celsius, then we know that the steam is what? Superheated, right? So let's check that now. So at 4 bars, using our saturated steam table, Tsat is given as 143.6 degrees Celsius. Now let's compare. The given temperature is 200 degrees Celsius. Since the given temperature is greater than the Tsat, than a saturated temperature, therefore the initial condition is superheated. Since the given temperature is greater than Tsat, therefore our steam at the initial condition is superheated. Okay, let's write that down. Since T is greater than Tsat, the steam at the initial condition is superheated. Okay, next we know that since it is a superheated steam, we now move over to our superheated steam table, and in calculating the volume for a superheated steam, we have that V1 is given as mass times Vg1, right? So we search for Vg1 at 4 bars in a temperature of what? 200 degrees Celsius. Using our superheated steam table. Okay. Therefore, VG1, which is same thing as saying VG at 4 bars in a temperature of 200 degrees Celsius is equal to from our superheated steam table, this is equal to 0.5345 meter cube per kilogram, right? Okay, that is that. From this we can get our mass. From this we can get our mass. So let's get our mass. We know that V1 was given as 0.5, and we've gotten a value for VG1, which is what? 0.5345 m. Now, dividing both sides by the coefficient of m, we get the value of m. So this is it. The coefficient of m here is 0.5345. So let's divide both sides by this. Therefore, m equals 0.935 kilogram. So this gives us the mass of the steam. Mind you, we've not still gotten the quality of the steam. So let's go over to the final condition. Let's check for the final condition. Final condition. Also recall that since you are asked for final quality, that is your dryness fraction, therefore you should know that that steam should be at a saturated steam in order for you to get the final quality. So let's check for that. For the final condition, we have that V2 is given as 0.1 meter cube. Since we have a constant pressure, we know that P2 remains constant, which is 4 bars. For this, we are still having a total volume. In order for us to use as steam table, as I said, as I've been talking about, as I've been saying, we need to have a specific volume. And in getting your specific volume, you need to divide by mass. Therefore, V2 divided by m equals 0.1 divided by our mass, which we've gotten as 0.935. Therefore, a specific volume V2 equals 0.107 meter cube per kilogram. So let's check the condition of the steam in the final condition. Okay, let's check for that now. So let's check for Vg at 4 bars. If it is greater than this, then our steam is said to be saturated. So let's check for Vg at 4 bars using a saturated steam table. What do we get? We get that Vg at 4 bars equals 0.4623 meter cube per kilogram, right? Okay, let's compare. This Vg is greater than the specific volume given. Therefore, our final condition is a saturated steam. Okay, let's write that down. Since Vg is greater than a specific volume. Hence, the steam is saturated, and we go back to our saturation steam table, our saturated steam table. So let's get that now. We know that the volume for a saturated steam is given as V2 xmVg2. Now Vg2 is Vg at 4 bars, which we got as 0.4623. Okay. Now we know our value for V2, right? Yes, we know our total volume V2, we know our mass, and we know our Vg2. Therefore, we can get our dryness fraction, or the final quality of the steam. Therefore, this is gotten as, okay, what was our V2? 0.1, right? Equals X, our dryness fraction or final quality, multiplied by our mass. Our mass was gotten to be 0.935. 0.935 multiplied by our Vg2, 0.4623 multiplied by our dryness fraction or final quality, X. Okay, multiplying that, we get that this is equal to 0.4322x. So how do we get the value of x? We divide both sides by the coefficient of x. Therefore, we have that 0.1 divided by 0.4322 equal to 0.4332x, all divided by 0.4332x. So let's go. This cancels out. Okay. By the coefficient of x, this cancels out, and x is left. Therefore, 0.1 divided by 0.4322 gives us 0.2313, right? This gives us our dryness fraction or final quality of the steam. Next, from the question, we are asked to calculate the work done. Okay, the work done for a constant pressure process is given as P as W equal to P multiplied by the change in volume, right? Now let's calculate for that. I, work done. The work done for a constant pressure process, W, is given as P dV, which equals P V2 minus V1. Okay, let's do that. Mind you, I said you don't work with your pressure in bar. So if you're given a pressure in bar, you do what? You convert it to Pascal or Newton per meter square. So in converting to Pascal, you just have to multiply by 10 raised to power 5. Therefore, this gives us that our pressure is given as 4 times 10 raised to power 5 bracket. What was the V2 given? The given V2 was 0.1 minus 0.5, and this gives us 4 times 10 raised to power 5 minus 0.4. In multiplying this, we have that our work done gives us minus 1.6 times 10 raised to power 5 joules, which is the same thing as saying minus 160 kilojoules. Okay, this is our final answer. It can be seen that work is done on the system. Work is being done on the system. Okay, next up, we are asked to calculate the heat transferred during the process. Heat transferred during the process. So how do we calculate heat transfer during this process? I, heat transferred. Recall that from your steady flow energy equation, you have that Q minus W gives you the U, right? Right? Okay. Therefore, the heat transfer Q equals the U plus W. Okay, let's do that. Now, what is the U? The U is change in internal energy, right? So the U equal U2 minus U1. So let's get that now. Let's get that. For the final condition, what is our internal energy? And for the initial condition, what is our internal energy? We know that for our final condition, we are having what? A saturated steam, right? So we calculate the U2 using our saturated steam table. And for the initial condition, which we had as a superheated steam, we calculate U1 using our superheated steam table. So let's go. Now, for the initial condition, U1 is given as MUG1. Remember, it is a superheated steam at the initial condition. Therefore, this formula was given for the internal energy of a superheated steam. U1 equals M multiplied by UG1. Now we know our mass. What are we searching for? UG1. Okay, for the superheated steam. So let's go. We know that UG1 equals UG at 4 bars in a temperature of 200 degrees Celsius. So let's check using our superheated steam table. we have that this equals 2648 kilojoules per kilogram, right? Yes. Okay. Next up, therefore our U1 can be gotten, right? We've gotten the value for this and we know what our mass is. Therefore U1 equals, our mass was gotten to be 0.935 multiplied by UG1, which is 2648. Therefore our U1 equals 2475.88 kilojoules. That gives us the value for our U1. Next up, let's calculate our U2. In getting our heat transfer, we've already gotten our work done. Next we needed was our du, right? Our change in internal energy. And we've gotten the value for U1, so we are left for the value of U2, which is what? At the final condition, it became what? A saturated steam. So we are to solve U2 using our saturated steam table and a saturated steam formula for internal energy. Okay, let's do that. Now, for our saturated steam, we know that U2 equals M bracket X UFG plus UF, right? So this was given for the internal energy of a saturated steam. So what do we have? We have this. We know our final quality or dryness fraction X. So what are we searching for? This and this. So let's check for UF at 4 bars. UFG at 4 bars using your saturated steam table. Saturated steam table, not superheated steam table. Since our final condition is a saturated steam. Therefore, this gives us 1949 kilojoules per kilogram, right? UF at 4 bars gives us 605 kilojoules per kilogram. Therefore, our U2 equals, what's the mass? Our mass was gotten to be 0.935 in brackets. We have, what was our X? Our X was gotten as 0.2313 multiplied by UFG 1949 plus UF. Our UF is gotten as 605, right? So we close our brackets. So this is it. So in simplifying, we got that U2 equals, now this is it, this is how we go. Okay, 0.935. Simplifying this bracket, we multiply this first, then we add this, and we get 1055.80. Therefore, our U2 equals 987.18 kilojoules. Therefore, the U equals U2 minus U1. U2 minus U1. The U then equals 987.18 minus 2475.88. Therefore, the U gives us minus 1488.7 kilojoules. Now we can get our heat transferred. Heat transfer was given as Q equals du plus W, right? Now our du is minus 1488.7, and our work done was given as minus 160 kilojoules. So we added them. We had that minus 1488.7 plus minus 160. Plus times minus gives us minus. Therefore, our heat transfer Q equals minus 1648.7 kilojoules. So this is it. We've actually worked on that particular question. We've gotten our final quality, and as I said earlier, your final quality is your dryness fraction. Don't get confused. Whenever you are asked for final quality, you should know they are talking about dryness fraction. We've calculated for our final quality, which is our dryness fraction, the work done, and the heat transferred. So it will be better if you revise the notes. Then this question will be very simple. Thank you. Okay, welcome. Question 5b. From the first principle, show that the change in entropy for a perfect gas is given by the expression Okay. Show that from first principle, the change in entropy is given with this is given by the expression. Okay, let's do that. Now we know that for a unit of a perfect gas, okay, son. We know that for a unit of a perfect gas, PV equals R root T, right? Let's call that equation 1. And we also know that from our non-flow energy equation that the Q equals du plus P dV. You might ask how. We know that Q minus W equal to du, right? From our non-flow energy equation. Therefore, Q equals du plus W, right? So a change in Q leads to a change in work done. Then the Q equals du plus P dV. Okay. Let's call this equation 2. This is from our non-flow energy equation. But du is equal to Cv dt. But du is equal to Cv dt. From equation 1, we know that P equals root T over V, right? Substituting it into equation 2, we get that substituting this into 2, we get that the Q equals Cv dt plus RT dV, right? Let's call this equation 3. Dividing through by T, next up we divide through equation 3 by T. We have that the Q dividing through, we have that the Q over T equals Cv dt over T plus T cancels out. We have R dV over V. Next up, integrating equation. Let's call this equation 4. Now let's integrate this. Let's integrate this. Integrating through equation 4 or integrate equation 4. We get the Q over T equal to the integral of Cv dt over T plus the integral from V2 to V1 Ru dV over V. Therefore, the S, this gives us our entropy concept, which is what? Change in X. The S equals Cv integral of this. Cv is a constant, so it goes at the integral sign to give us this, the T over T plus R is a constant, right? It comes out and we have this, dV over V. So integrating this, we have that the S equals Cv ln t, right? Between the upper limit and the lower limit, plus r ln v. The s equals cv. Integrating this gives us ln. Okay, welcome back. Sorry, there was a technical glitch. Okay, let's start from here. The s is equal to cv ln t after integrating 1 over t. We had this. So plus r ln v after integrating this to the limit v2 v1 and this to the limit t2 t1. So therefore the s equals cv ln t2 upper limit minus the lower limit t1 plus r ln v2 minus v1, which is also your upper limit minus the lower limit. Therefore the s equals cv ln t2 over t1 after applying your law of indices plus r ln v2 over v1, still on the application of the law of indices. Now, recall that for a perfect gas, P1 V1 over T1 is equal to P2 V2 over T2. Rearranging this, we get that T2 over T1 equals P2 V2 over P1 V1, which is the same thing as saying P2 over P1 multiplied by V2 over V1. Okay, next we impute that into we substitute that into our equation 5 for the value of T2 over T1. Therefore, we get this, that the S, which is a change in entropy, is equal to CV ln P2 over P1 multiplied by V2 over V1 plus R ln V2 over V1. So let's multiply through the bracket. We get that CV ln CV multiplied by this, we get CV ln P2 over P1 plus CV. Okay, from the laws of indices, this can be separated to give us CV ln P2 over P1 plus ln V2 over V1 plus R ln V2 over V1. So multiplying through by CV, we get that CV ln P2 over P1 plus CV ln V2 over V1 plus R ln V2 over V1. Simplifying this, since this and this both carries ln V2 over V1, we can actually factorize. So in factorizing, we get CV ln P2 over P1 plus CV plus R after taking out ln V2 over V1, which is common for both of them. We get this CV plus R ln multiplied by ln V2 over V1. So rearranging, we get that, okay, I brought this first plus CV ln P2 over P1. Always remember that our aim is to get this, is to prove that the change in entropy is given as Cp ln V2 over V1 plus bracket Cp minus R ln P2 over V1. Now recall, recall that Cp equals Cv plus R, and Cv therefore equals Cp minus R, right? So let's substitute that into this equation. Let's call this equation 6. Let's call this equation 6. Let's call that equation 6. So we can see that Cp equals Cv plus R, and from our equation 6 we have Cv plus R, right? Therefore the S equals Cv plus R, which is what? Cp ln V2 over V1 plus Cv is given as what? Cp minus R, right? Cp minus R ln P2 over P1, right? So let's compare. Comparing this to what was given in our question, then it is being answered, since we have proven that the change in entropy, which is the S, is equal to Cp ln V2 over V1 plus Cp minus R ln P2 over P1. So this has been proven.